Gravity. As we've discussed in class, we have to change the force of gravity. The old school way, we just said the force of gravity, often referred to as our weight, was just mg, and then the potential energy due to being in a gravitational field was mgh. Well, now the force of gravity is the big boy version, gmm over r squared, where m and m are just the two separate masses. I usually use one capital M and one little m to denote the fact that we're typically talking about a planet and a satellite, but really it's just m1 and m2. G is the universal gravitational constant, which is up here, and you don't need to memorize that. That'll be given to you. And then r is the distance between the masses. This is often referred to as an inverse square law because the distance is in the denominator, and of course it's squared. Well, once we redefine that the force is some function of the distance, so the force of gravity changes as we move further and further away from the planet, well, then we are also then required to change the potential energy function. And these two work really well together. The potential energy, instead of going from 0 to infinity with our old school mgh, it now starts at a negative value when you're on the surface of the planet, and then it grows asymptotically towards a potential energy of 0 as you get farther and farther and farther away, which is where this limit would come into play. The limit of the potential energy as you get so far away from the planet tends to 0. Side note, the force of gravity is the negative derivative of the potential energy, and that should make sense. The increase of potential energy is due to the fact that you have to do work on something, and so you're doing work against the force. So the force, of course, has to be in the opposite direction of the increase of potential energy, and that's always been true. If you also even just true for a spring, if you increase the potential energy of something, you're doing work against a force pointing in the opposite direction. Okay, so I guess the first thing most people want to look at is just orbital motion. So here's our planet, big M, and we got a little satellite or a moon orbiting this planet in nice circular motion. We want to remind ourselves it's circular motion. So the velocity is tangent, the acceleration is inward, thus the force is inward. And in this case, the only force acting on a satellite is gravity, and gravity is pulling it inward. So if you do F equals ma, start with F equals ma there, the force is gmm over r squared, circular motion is mv squared over r, and that allows us to find the orbital speed of a satellite, right? It's proportional to the mass of the planet and how far you are away in terms of orbit, and it's the square root of those. What you can do with that, you can take this and get Kepler's third law really quick. So Kepler's third law is going to say that the period squared is proportional to r cubed, and what you do is you just start with that. And that is no more than just saying that the time it takes to go around something is the distance divided by the speed. And so if you take the distance of 2 pi r over v and you square both sides of this equation, you're going to get t squared 4 pi squared r squared over v squared. And then you can come up here and put that v in, square it, and then simplify, and then you get Kepler's third law. Okay, so if you want to get Kepler's third law, or you want to look at orbital speed, you're simply looking at a circular the fact that a satellite is moving in circular motion around a planet. The gravitational force is the one causing it. It is inward, and then you go from there. Just as a reminder, none of these values, g, the mass of the Earth, the radius of the Earth, the mass of the Sun, the mass of the Moon, none of these need memorized. They're all either given to you in the problem, or they're actually just on the formula sheet on the AP. Okay, so that was orbital velocity. Now let's talk about escape velocity. So we're on planet Earth. This is our planet Earth. And you're like a golf ball, and boom, you're going to smack it. And you want it to get going so fast, launched so fast, that it escapes Earth's gravitational field. That is just a conservation of energy idea. So you're going to give it some kinetic at the beginning. That's the potential energy it has while on the Earth's surface. And if you want it to escape, you actually want it to have a final energy of 0, right? It's going to end up with no kinetic energy because remember, we're launching it with a minimum speed to escape. If we launch it faster than that, then it'll have kinetic. So we basically want to launch it just fast enough that it just starts to float away and go forever. And so both the potential energy and the kinetic energy are zero, and you solve that equation and you get the escape velocity formula, which looks really similar to orbital velocity, except there's a 2, and this is a capital R. Capital R being, it's the radius of the planet you're being launched from. Okay, if they wanted to know the total mechanical energy of a satellite in stable circular orbit, then you know that the total energy is a combination of kinetic and potential. Kinetic is 1/2 mv squared. Potential is that. However, if you go back up here and you look, well, this is the orbital speed. So you can actually take that value for v and chuck it in for v. And when you simplify, these end up being both like terms. You end up getting this. You can memorize that if you wanted to, but that is the total energy of a satellite in stable circular orbit. And you can notice that it's negative. It'll always be negative because the potential energy will always end up being negative, and it'll be double the kinetic energy. And so when you combine those, you get that -1/2. And then really the last thing we look at when we look at gravity, right? We look at the force of gravity, potential energy of gravity, circular motion due to being in gravitational field, orbital speed, Kepler's third law, escape velocity, total energy, and last, now we look at elliptical orbits, right? And this would be kind of Kepler's first law. The idea of what's happening when this satellite orbits, you're like, satellite, comet, probably a comet's probably better to think about in this case. As we go around there, there's no torque. Why not? Well, torque is an R cross F. There has to be some perpendicular component to the force. And in this case, the R hat direction is straight to the satellite, but that's the exact same direction that the force of gravity is pulling. The force of gravity is pulling inward. R hat is inward. There's no perpendicular piece. So there's no torque. If there's no torque, the system cannot get a change in angular momentum, which means angular momentum is conserved, which means you can write this statement. At position 1, it's got m v1r1. At position 2, it's got m v2r2, and those quantities have to be equal. And what it really means is when you're further away, you're moving slower. If you're closer, you're moving faster. And I would add the fact that there was an AP question one time that asked about omega. But if L1 equals L2, then you could also write, that's not going to let me write that very well, but you can put it in your notes. You can also write I1 omega 1 equals I2 omega 2, and you could actually compare the angular velocities at positions 1 and 2. Making note the fact that I has an R squared in it, so be careful. It's not linear. This guy's linear, tripling the distance cuts the velocity into a third. It's not the same thing for I and omega because the I has an R squared in it and ends up being squaring that factor. So if you double the R, you actually reduce the omega by a quarter. So they can ask you about omega, but generally with elliptical orbits, they ask you about the velocity or the ratio of the velocities based on the ratio of the distances. So angular momentum, energy, circular motion, forces, and potential energy graphs. Definitely, they love the double, triple type questions on multiple choices like this. They say planet X, some new planet has 5 times the mass and twice the radius. What's gravity on that planet? And you're like, oh, you're multiplying the mass by 5 and the radius by 2, but then you're squaring it in the denominator. Oh, that just means that the force of gravity is 5/4 of Earth, which means the acceleration due to gravity is then 5/4 of g. And so you can do all sorts of questions like that. They can ask you center mass questions. So like, here's the mass of the Earth, there's the sun, where's the center mass? And you just do the center mass equation, which says that the center mass is m1 x1 plus m2 x2, all divided by the total mass, which is just basically a weighted average of the two masses based on their position. So hopefully this is a good review, but they definitely, if you know the formulas, you can definitely do the double, triple questions much faster on the multiple choice. So please put some of these in memory. Just as a note, these two right here, these two are the only two that are actually on the AP. All these other ones, orbital velocity, escape velocity, total mechanical energy, conservation of angle, those are not given at all. those are things you'd have to either derive on a free response question or just know instantly on a multiple choice.